I was a graduate student at Princeton when my professor called me with the craziest idea I had ever heard. He said, "Feynman, I know why all electrons have the same charge and the same mass." I asked, "Why?" He said, "Because they are all the same electron. One electron bouncing back and forth through time, appearing everywhere at once." I thought he had lost his mind. 25 years later, that phone call helped me win the Nobel Prize. Here is the problem Wheeler was trying to solve. Every electron in the universe is exactly the same, not similar, not nearly identical, exactly the same. Same mass, same charge, same spin, down to the last decimal place. Look around you. Nothing else in nature works like this. No two snowflakes are the same. No two grains of sand. No two stars. But electrons? There are something like 10 to the 80th power of them in the observable universe. That is a 1 with 80 zeros. And every single one is perfectly identical to every other one. Nobody could explain why. We just accepted it as a brute fact. Electrons are identical. The end. Move on. But Wheeler didn't move on. Wheeler wanted to know why. First, you need to understand who John Wheeler was. When I arrived at Princeton in the fall of 1939, I expected to work with Eugene Wigner. Wigner was a giant. He would later win the Nobel Prize, but when I showed up, they told me I had been assigned to someone else, a young professor named John Archibald Wheeler. I had never heard of him. Wheeler was only 28 years old, just 7 years older than me. In academia, that's nothing. Most professors were ancient men in three-piece suits. Wheeler looked like he could be my older brother. What could this young guy teach me? Everything, as it turned out. Wheeler had already collaborated with Niels Bohr himself. Together, they had written the definitive paper on nuclear fission, the paper that appeared in Physical Review on September 1st, 1939, the very day Germany invaded Poland. But that wasn't what made Wheeler special. What made Wheeler special was the way his mind worked. He looked completely ordinary, soft-spoken, conservative clothes. He could have been a banker, but inside that calm exterior was the wildest imagination I ever encountered. Wheeler would say things that made other physicists uncomfortable, things that sounded more like science fiction than science. He would later give us words like wormhole and black hole. Other professors played it safe. They worked on small problems. Not Wheeler. Wheeler asked the dangerous questions. The questions that could make you look like a fool. And he treated me like an equal from the very first day. Not like a student, like a colleague. "Feynman," he would say, "what do you think?" So one day, the phone rang. It was Wheeler. He told Feynman that he knew why all electrons have the same charge and the same mass. Feynman asked why. Wheeler answered that they are all the same electron. Then Wheeler started explaining. Wheeler suggested that the world lines we were ordinarily considering in time and space, instead of only going up in time, were a tremendous knot. I tried to picture what he was describing. He said that when you cut through the knot, by the plane corresponding to a fixed time, you would see many, many world lines, and that would represent many electrons. In physics, we represent particles as lines moving through space and time. A world line. An electron starts here, moves there, exists across time as a continuous line through the universe. Wheeler was suggesting something incredible. What if there was only one electron in the entire universe? Just one. But that single electron was not moving in a straight line through time. It was bouncing back and forth, forward and backward, weaving through the history of the universe like a thread through cloth. At any given moment, when you slice through time, that one electron would appear in billions of locations. It would look like many electrons, but they would all be the same electron, just at different points in its journey. That is why they are all identical. They are not similar. They are literally the same particle. Then Wheeler said something else. If in one section, this is an ordinary electron world line, in the section in which it reversed itself and is coming back from the future, we have the wrong sign to the proper time. And that is equivalent to changing the sign of the charge. I understood immediately. You mean when it goes backward? It looks like a positron. Exactly. A positron. The antimatter twin of the electron. Same mass. Opposite charge. Carl Anderson had discovered it in 1932. Wheeler was saying that positrons were not a different kind of particle at all. They were just electrons traveling backward through time. This was beautiful, elegant, insane. And I immediately saw a problem. "But Professor," I said, "there are not as many positrons as electrons. If his theory was right, every time the electron bounced forward in time, it would look like an electron. Every time it bounced backward in time, it would look like a positron. The numbers should be equal, but they are not. There are vastly more electrons than positrons. Positrons are rare. Most of the universe is made of matter, not antimatter." Wheeler's one-electron universe required equal amounts of matter and antimatter. "Well," Wheeler said. He paused. "Maybe they are hidden in the protons or something." That was his answer. Maybe the missing positrons are hidden somewhere. I loved Wheeler, but that answer was not very convincing. Here is what I learned that day. I did not take the idea that all electrons were the same one very seriously. The math did not work out. There were too many electrons and not enough positrons. Wheeler's beautiful theory was probably wrong. But buried inside his crazy idea was something else. Something that was not wrong. Something that would change physics forever. Positrons could simply be represented as electrons going from the future to the past. That I stole. Not the one-electron universe. That was too far out. But the idea that antimatter was matter moving backward in time, that was something I could use. Let me explain why this mattered. Before Wheeler's phone call, we thought of electrons and positrons as two different kinds of particles. We had one set of equations for electrons and another set for positrons. The mathematics was complicated, messy. But if positrons were just electrons moving backward in time, everything became simpler. Instead of two particles, we had one particle doing two things. Instead of two sets of equations, we needed only one. The mathematics collapsed into something elegant. I started seeing particles differently, not as separate objects traveling in one direction through time, but as lines that could twist and turn. Forward, backward. The direction did not matter. It was all the same physics. This was the seed. From this seed grew the diagrams. Little pictures I started drawing to help me think. Lines representing particles. Lines moving forward. Lines moving backward. Lines twisting and interacting. Years later, people would call them Feynman diagrams. But the core idea, that you could think of antimatter as matter moving backward in time, came from Wheeler. From a telephone call. From a professor who was not afraid to say something crazy. 8 years later, I tried to explain all of this to the greatest physicists in the world. It was the end of March, 1948, the Pocono Conference. 28 physicists gathered at a hotel in the mountains of Pennsylvania. This was the most intimidating audience imaginable. Niels Bohr was there, the father of quantum mechanics, the man who had argued with Einstein. Paul Dirac was there. His equation had predicted antimatter. He won the Nobel Prize at 31. Robert Oppenheimer was there, the man who had led Los Alamos, who had built the bomb. Eugene Wigner, Enrico Fermi, Edward Teller, Hans Bethe, everyone. Julian Schwinger spoke first. He talked for the entire day, from morning until evening, with just a brief break for lunch. His mathematics was dense, complicated, traditional. But the audience followed him. They understood. Then it was my turn. I stood at the blackboard and started drawing my diagrams. The little pictures that showed particles moving through space and time. The arrows going forward, the arrows going backward. Electrons turning into positrons, positrons turning into electrons. Nobody understood. Dirac kept interrupting me with questions. Cold, precise questions that I tried to answer. But he kept pressing. Teller raised objections. And then Bohr stood up. Niels Bohr, my hero, the greatest physicist of his generation. He said I had forgotten the uncertainty principle, that I could not draw these lines, that I could not talk about electrons having paths through space, that this was not how quantum mechanics works. He did not understand. The diagrams were not literal. They were a notation, a shorthand, a way of organizing calculations. But I couldn't explain it clearly. My presentation was rushed, chaotic. I was following Schwinger's marathon performance, and I was too excited, too scattered, too weird. After the conference, I was in despair. Later, I said I had too much stuff. My machines came from too far away. Nobody got it. The idea that had started with Wheeler's phone call, the idea of particles moving backward in time, no one could see what I saw. But here's the thing about physics. Eventually, the truth wins. There was a young British mathematician at Cornell named Freeman Dyson. He had arrived from Cambridge in 1947, one of England's most brilliant mathematical prodigies. At first, Dyson thought I was a bit of a buffoon. I didn't look like a serious physicist. I didn't act like one either. But then Dyson noticed something strange. Problems that took him pages of calculations I could solve in a few lines. He didn't understand how I was doing it. Nobody did. But he could see that I was getting the right answers. So he started paying attention. In the summer of 1948, a few months after my disaster at Pocono, Dyson and I drove across the country together. 4 days, 2,000 miles, Cleveland to Albuquerque. I was behind the wheel, all country roads. There were no superhighways yet. We got stuck in a rainstorm in Oklahoma. We got a speeding ticket in New Mexico. And the whole time we talked about physics, about life, about my diagrams. Dyson had me all to himself, and slowly he began to understand what I was doing. After we arrived in Albuquerque, Dyson went to the University of Michigan, where Schwinger was teaching a summer course. For 6 weeks, Dyson listened to Schwinger explain his approach, the complicated one, the one everyone at Pocono had understood. And then Dyson got on a Greyhound bus to Princeton. Somewhere in Nebraska, late at night, bumping along a dark highway, it hit him. Schwinger and I were doing the same thing. Different methods, different notation, different style. But mathematically, we were saying exactly the same thing. Our theories were equivalent. Dyson wrote it all down. His paper, The Radiation Theories of Tominaga, Schwinger, and Feynman, showed the world that my strange diagrams were not nonsense. They were a new language, a simpler language, a language that gave the same answers as Schwinger's complicated equations, but in a fraction of the time. Within a few years, everyone was using Feynman diagrams. They spread through physics like wildfire, not because they were more rigorous, but because they were more useful. You could draw them on a napkin. Graduate students could learn them in an afternoon. And buried inside every diagram was Wheeler's crazy idea. The lines going backward, the positrons that were electrons moving the wrong way through time. In 1965, I shared the Nobel Prize in Physics with Julian Schwinger and Shinichiro Tominaga. Dyson was not included. The Nobel Prize has a rule, no more than 3 people. In my Nobel lecture, I told the story about the phone call, about Wheeler's wild idea. I said I did not take the idea that all the electrons were the same one from Wheeler as seriously as I took the observation that positrons could simply be represented as electrons going from the future to the past in a back section of their world lines. That I stole. Here is what I learned from John Wheeler. The crazy ideas matter. Not because they are always right. Wheeler's one-electron universe was wrong. The math did not work. There are not equal numbers of electrons and positrons. But buried inside that wrong idea was a right idea. An important idea. An idea that changed how we think about matter and antimatter forever. Most scientists are afraid to sound foolish. They stay safe. They work on small problems with guaranteed answers. Wheeler was different. He would say the wild thing out loud. He would follow it wherever it led. And sometimes, buried inside the wildness, there was treasure. You cannot find new truths by thinking safe thoughts. You have to be willing to be wrong, willing to sound crazy, willing to follow an idea into the darkness and not knowing if it leads anywhere. Wheeler taught me that. He called a graduate student and told him that every electron in the universe was the same particle bouncing back and forth through time. It was probably wrong, but I am still thinking about it. If this story meant something to you, hit subscribe. I tell stories like this about the real lives of the scientists who changed our world. I'll see you in the next one.